Welcome. In this video, we conclude Unit 7, Polynomial Functions. We are in Day 2, the zeros of polynomial functions, and this section from the book is 5.1, and today we tackle Objective 3, identify the real zeros of a polynomial function and their multiplicity. The zeros of a function. Suppose that f of x is a function. It could be any function, it doesn't have to be a polynomial function. So this is true in general. Suppose f of x is a function. The zeros of f of x are those x values that make f of x equal to 0. For example, what are the zeros of this function? F of x equals x squared minus 2x minus 3. You might play around for a little bit. You plug in some numbers in for x and see if you can make that thing 0. But you get tired of playing around for a little while. You'd like a better method. And the better method is to factor the polynomial. Because now you can see, oh, if you actually plug in a 3 for x, then your answer is something times 0, and that's 0. Or, actually, if you plug in a negative 1 for x, then this first factor is 0. And so the whole thing becomes 0. So f of negative 1 is 0, and f of 3 is 0. The zeros of f are negative 1 and 3. Those are the zeros of my function, negative 1 and 3. The zeros of a function are where the graph touches or crosses the x-axis. So look at the picture. I've just drawn the picture of that function. And it crosses the x-axis at negative 1, and it crosses the x-axis at 3. This is worth putting in a box because it's pretty important. The zeros of a function are where the graph touches or crosses the x-axis. So if I know the zeros, I can start thinking about how to sketch it. And if I have a sketch of the graph and I see where it crosses the x-axis, that gives me information about the zeros. How would you graph f of x equals x minus 2 times x minus 4? Well, the zeros are at 2 and 4. 2 and 4. So I would identify 2 and 4 on the x-axis, and now it's a parabola that goes through 2 and 4. How about the next one? Make a sketch of g of x equals x plus 3, x plus 5. What are the zeros there? In this case, the zeros are negative 3 and negative 5. So I'll make some axes. I'll identify negative 5, negative 3, and I'll put my parabola so it goes through those 2 points. Now, how about y equals 10 times x minus 2, x minus 4? Look at the top. It's pretty similar to what I had before. What effect does that 10 have in front? That's a stretching factor. That will stretch it by a factor of 10 vertically. So I kind of have the same picture. It's the same zeros, 2 and 4, the graph still crosses it in the same place. But now the graph is stretched out way big. It's stretched out 10 times as much. And then lastly, how about this question? How would I sketch the graph? Oh, same zeros at 2 and 4, but now there's a negative in front. What effect does that have? Well, it's like I take the graph that's on top, the parabola that goes through 2 and 4, and I just flip it vertically. 2 and 4. And I make an upside down parabola. There we go, something like that. Oh, this is a tricky one. How would you sketch y equals x minus 1 times x minus 3 times x minus 6? Well, I know where the zeros are. The zeros are at 1, 3, and 6. 1, 3, 6. But how does the graph actually pass through there? So it might pass through the 1 and then up the 3 and down through the 6 like that. Or it might come up from the bottom through the 1 and down through the 3 and up through the 6 like that. Or it might just come down and touch the 1 and then maybe pass through the 3 and up through the 6. Or comes up and then touches there, then goes through. It's a little tricky. So we don't really know, and we will, over the next few minutes, we will develop the technique to figure this out. We don't know for sure, but at least we do know that whatever this graph looks like, it crosses or touches the x-axis only at those points. The multiplicity of zeros. So consider this function, f of x is x plus 7 times x plus 2 to the 6th power times x minus 4 to the 5th power. This function f has a 0 at negative 7, because if I plug in negative 7, the whole value of the function will become 0. And we say that this 0 has multiplicity 1. F also has a 0 at negative 2. If I plug in negative 2, the value of the whole thing goes to 0. But that negative 2, I say, has a multiplicity of 6. It's because this factor, x plus 2, appears 6 times. It's almost like the 0 of negative 2 appears 6 times on top of itself. And then lastly, f has a 0 at 4, and we say that that 0 has multiplicity 5, because the factor x minus 4 appears 5 times. Slightly connected to this is the question, what is the leading term of f? So you have to imagine, if you took f, if you multiplied it all out, and that would be a horrible multiplication. That'd be terrible. Don't do it. But if we did multiply it all out, at least could we determine what the leading term is? And we can. Here's what we do. Let's look at that first factor, x plus 7, and I'm going to pull out the x from there. And this next factor, x plus 2 to the 6th, if I multiplied that all out, I'd get a bunch of stuff all being added together, but at the very front of that, I would have x to the 6th. And then lastly, I look at this last factor here, x minus 4 to the 5th, and if I multiplied that all out, it would be terrible, but at the very beginning of it all, there would be an x to the 5th. Finally, I multiply those together, and when I multiply powers of x, I add the exponents. So 1 plus 6 plus 5, that's x to the 12. So the leading term of this function f is actually x to the 12. It's important to be able to identify the leading term because it tells us the end behavior of the function. X to the 12, do you know what that looks like? It's an even power, so something like this. So this function f, very roughly, it comes down, it does something, and then it leaves going up. And so it's kind of nice, at least knowing the leading term, it gives us the overall shape of this function. All right, so I'm going to pause here for a little bit. You try. Here are 3 problems. Find the zeros, find the multiplicities of the zeros, and find the leading term for each function. Pause the video now, try your best, and then start up again to check your work. Okay, here we go. For the first problem, the zeros are negative 2 with multiplicity 2 and 4 with multiplicity 5, and the leading term is x to the 7. In the second problem, zeros at negative 1 with multiplicity 1, 5 with multiplicity 6, and 10 with multiplicity 3. The leading term is negative 3 times x to the 10. Look at how that negative 3 stayed in there. So negative 3. That last one is a little bit tricky. Let's take a look at this first factor. Can I read off the 0? I can't just read the 0 off directly from that. But if I think to myself, 3x minus 1 equals 0, and then 3x equals 1, and so x equals 1/3, I see that 1/3 is a 0 of this function. And you can double check, right? If you actually plugged in 1/3 for x, then I'd have 3 times 1/3 is 1 minus 1, that gives me 0. And so this appears with multiplicity 2 because of that square. The other 0 looks like negative 6, and that appears with multiplicity 10. So 0 is at 1/3 and negative 6. What is the leading term of this thing? Leading term. Here's where I have to be a little bit careful again. What does this square do? It squares the entire thing. So in fact, this first 3x, that gets squared. So 3x, the whole thing being squared. And then for my second factor, that x just gets raised to the 10th power. Now if I expand out the 3x being squared, that's 3x times 3x times x to the 10. And now we can see the 3 times 3 is 9. And I have 12 x's there. So 9x to the 12. And there's my leading term. Does the graph cross or touch the x-axis at a 0? Let's determine that. How to sketch f of x equals that thing. So here's the idea. If a 0 has odd multiplicity, the graph crosses the x-axis there. And if a 0 has even multiplicity, the graph touches the x-axis there. Touches but doesn't cross. Something like comes up and touches and goes down, or comes down and touches and goes up. So what might the graph of f of x look like? So we see the zeros. Those are -7, -2, and 4. And the multiplicities of those are 1, 6, and 5. The leading term of this function is x to the 12. X to the 12 tells me the overall shape. And now, from this information, I can figure out a rough sketch of this function. So I will label the -7, -2, and 4. Those are the zeros. Now, I'm going to come down from the upper left. So I know that the graph starts coming down from the upper left because the leading term tells me the overall picture looks like x to the 12. Now, what will I do when I reach the -7? -7 has a multiplicity of 1, so I will cross the x-axis. All right, but now I need to hit the x-axis again at -2. What will I do when I get to -2? At -2, that has a multiplicity of 6, which is even, so I won't cross. I'll just touch and return. Touch and return. And now the graph will have to come, and it'll have to do something at +4. At 4, my multiplicity is 5, which is odd, so I will cross. In fact, it doesn't really matter. For what it's worth, it actually does a little bit of a level off trick and then continues on. The reason for this is because the x to the 5 looks like it levels off and continues on. So this sort of mimics the x to the 5 curve there. So there it is, a very, very rough sketch of that function. Let's do some more. What is the overall rule that I'm using to sketch functions? How would I sketch a function like this? So I determine the zeros and their multiplicity, find the leading term to show you end behavior, and then sketch. I cross the x-axis at zeros with odd multiplicity, and I touch, but don't cross, at zeros with even multiplicity. All right, let's try that here. So I will identify the zeros. Oh, look at this. This is something new. I just have an x here by itself. Not really, it's not like an x plus 2 or x minus 9. I guess you could think of it as x minus 0. That actually is a 0 itself. The x plus 1 gives me a 0 of -1, and the x minus 4 gives me a 0 that's 4. The multiplicity of these zeros looks like 1 and 4 and 2. What is the leading term of this polynomial? I have a constant out front of -3. I'll put that -3 there. How about my x's? How many x's do I have? I have 1 at the beginning, and then 4, and then another 2. So that looks like 1, 4, 2, maybe 7 x's. So what does -3 x to the 7 look like? I think to myself, x to the 7 is one of those odd power functions like that. Oh, but I want negative of that, so I need to flip it over. -3x to the 7. There we go. So this is the overall shape. This is the overall shape for the polynomial. Starts on the top left, and it will end up at the bottom right. I think I have all the information now to sketch. Okay, I'll make an x-axis. My zeros are at -1, 0, and 4. And let's start. I'll come in from the top left. I'm coming down towards that -1. When I get to -1, it has multiplicity 4, so I'm going to bounce back up. When I get to the 0, that has multiplicity 1, so I'll go right through it. And then when I get to the 4, oh, that has multiplicity 2, which is even. So I'll come back down there like a parabola. And there we go. That's it. So my polynomial comes down, touches at -1, comes up, it crosses right at 0, comes up, it just touches at 4, but then it comes back down. There. That's kind of cool that we can even do that, make a rough sketch like that. You try. Here are 3 problems. Pause the video, try your best, and then start up again when you want to check your work. All right, let's see what these look like. All right, I hope you got something similar to that. Now here are some variations. We continue the idea of sketching, but sometimes these little quirks come up. Let's take a look at number 1. Let's sketch this thing out. So I start off as before. I make my zeros, and I see that there's just a 0 is one of those, so 0 there. What do I do with x squared minus 5? Well, it's not a linear factor, so I need to do a little bit of work. Let's say x squared minus 5 equals 0, so x squared equals 5. X equals plus or minus the square root of 5. So I also have negative square root of 5 and positive the square root of 5. And the multiplicity for each of those is 2, 1, and 1. And then what does my leading term look like? I have an x squared and an x squared, so maybe x to the 4. X to the 4 has this overall shape. All right, so negative square root of 5, 0, square root of 5. Those are the zeros of the function. And I will come in from the top left. When I get to my negative square root of 5, this has odd multiplicity, so I'll pass right through it. There we go. When I get to 0, that has multiplicity 2, so I'll turn around like a parabola. There we go. And then when I get to the square root of 5, that has multiplicity 1, so I'll pass through there. There we go. And how about the last problem? Sketch g of x squared plus 3 times x minus 5. Zeros, well, I see that 5 is a 0. I'll just handle that right away. How about the other factor, x squared plus 3? So I need to do a little work. X squared plus 3 equals 0. X squared equals negative 3. Uh-oh, wait a second. X squared equals negative 3. That can't happen, at least not in the real numbers. There's no real number that squares to negative 3. So what I conclude is this factor does not tell me any zeros. It does not contribute any zeros to the function. No zeros. So the only 0 is 5. What is the multiplicity of that 0? It is simply 1. All right, the leading term. Well, even though this first factor didn't tell me any zeros, it still does contribute to the leading term. So I have two factors of x there and one factor of x over there. So looks like 3 factors of x altogether. So x cubed, which looks like this. So I know that the function overall starts on the bottom left, and it'll end up at the top right. Okay, so I have just a single 0 at 5. So I'll start at the bottom left, and it comes up. It'll cross through the 5. 5 has multiplicity 1, and then continue on. And there we go. Our last topic is to make a polynomial that contains a given point. We are working backwards a little bit. In this case, we are given the zeros, and we're also given one other point on the polynomial. And we have to figure out, can I make the polynomial function with those zeros that goes through that particular point? How would we do that? Well, here's our strategy. I know the zeros, -2, 1, and 3, so I can make my 3 factors, x plus 2, x minus 1, x minus 3. But also, there might be some other number out in front. I'm not sure. In fact, I'll have to figure out what that number is in order to make the polynomial pass through my given point. Also, there's more than one answer to this question. I could have powers on top here, x plus 2 to the 5th, x minus 1 to the 7th, x minus 3 to the 10th power, and it would still have the proper zeros, but let's not do that. Let's just make this answer as simple as possible. So we'll just make all of our zeros have multiplicity 1. Okay, I have my zeros, and now I need to figure out what that a is. And I use the fact that since 4, 6 is a point on the polynomial function, this tells me that f of 4 equals 6. So let's figure out f of 4. F of 4, I'm just going to take the x and replace the x with 4 everywhere. So the a stays a, x plus 2 becomes 4 plus 2, which is 6, x minus 1 becomes 3, x minus 3, 4 minus 3 becomes 1. I multiply them all together, I get 18a. So f of 4 is 18a. Oh, but also f of 4 is 6, right? Since f of 4 is 6, this tells me that 18a equals 6. And now I can solve for that a. Now I know that a equals 1/3. So here is the actual function now. This is a function, f of x equals 1/3, x plus 2, x minus 1, x minus 3, and it has two nice properties. It has zeros at -2, 1, and 3, and because I chose my a just right, it also goes through the point 4, 6. All right, we have talked a lot about polynomials today and how to sketch them and their different properties and the zeros. There are some really interesting ways that the zeros of a polynomial relate to the graph of that function. So be sure you look back, review these ideas, think about it, and be sure to let me know if you have any questions.